Hello. Hello, hello. Yes. So, hey. So tonight is gonna be the midterm 3 review session for Helix class. Are you guys feeling ready for it? How are you guys feeling? Let's see. So I posted note card for you guys to use to print out if you guys want to, or like to see for inspiration if you guys want to use it to make your own note card. The front page here is like 3 copies of the front page of the note card. So if you print it out on that page in color, it's going to be in the correct dimensions, 3x5. So this front page here is going to have Diel's order. Right. Yeah. This midterm right here, like I would say it's a little bit like doable, but the hardest part I would say is the Diel's order reaction with the endo rule and the aligning the charge. So this is the Diel's order section. Another confusing thing might be the electrocyclic ring opening, ring closing, which is that section right there. The aromaticity chart is going to be this, like anti-aromatic, non-aromatic versus aromatic, and the differences between EDG and EWG is here as well. Now, the back page of the note card here is going to have the benzene reactions, right? Here is going to have halogenation. Here is going to be nitration, sulfonation.
Oh my god,
Here's
yeah,
going to be
that'd be so cute.
alkylation. And here's
Wait,
acylation. And here are the helper reactions for the benzene. Right. So do you guys have any questions or topics you guys want to go over before we get started? I did also post the worksheet here with the key as well, and I also have
wait, hold up.
winter 2023 practice midterms A and B, sections A and B from winter 2023. Current rotatory and dish rotatory synthesis, number 12 on predicted product, naphthalene reactions. Synthesis. Okay. Okay, so yeah, we'll definitely do a lot of synthesis problems today. Let's do number 12 on my predicted product first and go from there. Okay, so number 12 right here is Diel's order. This is the diene part of the molecule, right? S is diene. This is the this is the diene part. This is the dienophile part of the molecule right here, right? Which I'm gonna highlight in blue. And now I know that this is an EDG, this is an EDG, and this is also an EDG right here. So because these are R groups right here, there's going to be a negative charge equally on both sides of the carbon. So there's going to be a negative charge here and a negative charge right here, right? Because this, like imagine it as an EDG that can actually donate electrons into the system. That would give a negative charge on that carbon from this EDG. If we have this EDG right here, this EDG can donate electrons into the diene, giving a negative charge on that carbon right there. So we're going to have a negative charge on this carbon and a negative charge on that carbon. So now we look at the dienophile. This CN here is my EWG, right? Because if I draw out the CN out, it has a triple bond between carbon and nitrogen right there, which when we draw resonance, we're going to have a positive charge on the other end right there, right? And in this case, the charge alignment does not matter here because the negative charge aligns with the positive charge already, right? The negative charge on the bottom here aligns with the positive charge on the bottom. So we could continue with the Diel's order reaction. And I'm going to number this atom 1, this is 2, this is 3, this is 4, this is 5, this is 6, to give me this Diel's order product right here, right? Where this is 1, 2, 3, 4, 5, 6. And now when I figure out my out and in groups, right, it's always going to be on carbons 1 or 4, right? When you have groups on 2 or 3, that's not going to be an out or in group. I see that these groups here are out groups because they are facing outside of the pocket that I just drew in between the diene and dienophile, outside of the bubble between the diene and dienophile, right? Whereas this group right here is the in group because it's inside of the bubble, inside of the pocket. I think my internet is kind of lagging right now, so let me connect to my different Wi-Fi really quick. Right, let's see here. Is my EWG. And the endo rule states that the out group is cis to the EWG, and the in group is trans to the EWG. So for Helix's class, because the charge is already aligned, right? We don't have to flip any diene or dienophile. Let's say that my outgroups here on carbons 1 and 4, those methyl groups are dashes. If those methyl groups are dashes, then this CN here would also have to be a dash to follow the endo rule, right? Because we want the outgroups to the EWG. Now, we see there's a CH2 in between the 1 and 4. So I'm going to draw that CH2 like that, where it's going to be wedges because they're going to be trans to the CN. And now we look at the dienophile, this alkene right here. We see that there's an ethyl group here that is trans to this CN, and we have to maintain that trans configuration. So because the ethyl is trans to the CN, I have to draw the ethyl group wedge because the CN is dash, right? And then we could have a plus minus here. So for Helix's class, if you draw that, that should be full credit, right? But the other product that you can see here is that if you flip the dienophile upside down, you could get this product here instead, where this is the dash methyl, this is the wedged CH2 ring, and the CN would be on the bottom instead, and the ethyl would be on top instead, giving you the other set of enantiomers as a product. And the reason why we were able to do that is because this dienophile here, positive charge, is still aligned with the negative charge on the diene right there. So this is going to give you the other product. For Helix's class, I've seen some problems where he just like gives that one answer right there instead of this other answer here, right? Any questions on this Diels order problem? Like anything about the endo rule, the charge alignment, the dienophile configuration, how they trans to each other? Can you go over why the inner part is a wedge again? Yes. So the inner part here is a wedge because based on the endo rule, the in group is trans to the EWG. The out group is cis to the EWG, right? And when I figure out my out and in groups, the out and in groups are always going to be on carbons 1 and 4 on the diene, right? When you have groups on carbons 2 and 3, 5 and 6, they're not going to be considered out or in groups. The out and in groups are going to be on 1 and 4 only, and that's why I draw the pocket between the diene and dienophile like that to figure out what my out and in groups are. These groups here are going outside of the pocket, making them out groups. This in group here is inside of the pocket, making that the in group, right? And based on the endo rule, the in group is trans to the EWG. So because my EWG here is dash, the in group would have to be wedge to follow the endo rule, right? So that's why my in group is going to be wedge if my EWG is a dash, because I want my in group to be trans to my EWG, right? Okay. Any questions on this Diels order problem? Any other questions? Okay, so let's go over conrotatory and disrotatory reactions. So this is one example right here, number 11. So there's a chart that I use for these conrotatory, disrotatory reactions, right? And I'm gonna copy that chart over from the doc card that I shared with you guys right here. Like this is electrocyclic ring opening, ring closing. copy. And the procedure is going to be different if we are ring opening versus ring closing. So let's look at this example right here where we are going to do ring. Would you guys say this is ring opening or ring closing based on this structure here, looking at this structure here? Ring opening, yes. The note card could be on the Discord, or I will post it later on after the session as well. Yeah, this is ring opening, right? So the arrows of ring opening here are going to be like this. I'm going to shift this double bond over here to make a double bond there. This bond right here between the two chiral centers is going to break, and that's the ring opening part, to create a double bond right there, which is going to shift that double bond over to make a double bond right here, right? So if I number this molecule 1, 2, 3, 4, 5, 6, that's going to be this backbone right here, where I have this as my 1, 2, 3, 4, 5, 6 backbone right there. Carbons 3 and 4 stay flat and planar, sp2 hybridized. So I'm going to keep them as flat and planar. That ethyl group is flat, this methyl group is flat. Right? Now, we have this methyl group and propyl group that was wedge and dash, but it can no longer be wedge or dash because it became sp2 hybridized. Carbons 1 and 6 became sp2 hybridized. So the methyl group would either have to go up like this or down like that. The propyl group would have to go down like that or up like this. And to figure that out, we have to use this thumb rule here, right? So because we see 3 pairs of electrons moving here, that is going to be an odd pair of electrons. And when we have an odd pair of electrons reacting with light, H nu, this is going to be a con-rotatory reaction, right? And what con-rotatory and what this rotatory means is the direction that we rotate our groups in, right? So let's do the thumb rule. Because we're ring opening here, I'm going to start my thumbs up or down, and I'm going to end my thumbs left or right, right? So let's say my left thumb right here is the methyl group going up. I know it's going up because it's a wedge. And let's say my right thumb is going down because it's a dash. The propyl group is a dash going down, right? So because this is con-rotatory, I have to rotate my thumbs in the equal direction, in the same direction, right? So if I rotate my left thumb clockwise, right, I'm going to stop going here to the right. I don't rotate my thumb all the way going down, right? I just keep rotating until I go either right or left. So just rotate 90 degrees, right? So rotate 90 degrees is going this way. Because this is con-rotatory, I am also going to rotate my right thumb clockwise. And I see that they're bumping into each other. So that's one of my products. So I'm going to draw that out right here. So that's going to be if this methyl group is going down and this propyl group is going up, right? So that's one of the products. But I could also have, like, let's say this is the methyl group going up, this is the propyl group going down. If I rotate my left thumb going counterclockwise, and this thumb also goes counterclockwise, they're going away from each other now, which gives me this product right here. And I see that this is my major product, this is my minor product, because this has more steric hindrance, which we don't want, right? So this right here is going to be my major product for this ring opening example. Any questions on the procedure of how I got to that major and minor product? Any questions on the thumb rule, how I rotated them, how I started my thumbs, how I ended my thumbs for this particular problem? Okay, so yes. Which problems did we already go over? We went over number 12 of the worksheet, the Diels order reaction. Now we're going over number 11, the electrocyclic ring opening, ring closing, right? We went over ring opening. Now I'm going to go over ring closing. So let me find that ring closing example here. Let's look at number 2, for example. You're counting pairs of moving electrons, not pi electrons. Yes, right? That's a common misconception. When you do this electrocyclic ring opening, ring closing right here, you think that you are going to always count the pi electrons, right? The pi bonds, but that's not the only one that counts. It's also this sneaky bond here, right? That sneaky bond counts as a pair of electrons that is moving in the reaction. So in ring opening reactions, that counts as a pair of electrons right there. Naphthalene reactions, yes, I could go over naphthalene reactions later, but that's more of a predictive product thing and it's very quick, right? Actually, I could go over that now before we move on to that right there. So let me actually look at the naphthalene reactions that Helix wants you to know here. Right, let's see. And this is more for predictive product, I would say. So let's say, let's do week 8-5, naphthalene, right here, yeah. Okay. So naphthalene is gonna have 2 benzene rings fused together like that, right? And if we have an EDG attached to the naphthalene and we put some kind of electrophile with a catalyst attached to it, and it's going to be different for any EAS reaction, like nitration, sulfonation, halogenation, phytocast alkylation, phytocast acylation, the electrophile is going to go attach opposite to the EDG, right? So based on this naphthalene reaction here, we're going to have the electrophile attached to this carbon here that's opposite to the EDG. Now, if you have an EWG attached to the naphthalene, and you react it with an electrophile, an EAS reaction, the electrophile is going to attach to this carbon right here, right? So this is more commonly going to be shown in predictive product problem. Let me give you an example problem here, right? So let's say I have this benzene ring reacting with Br2, FeBr3, and I have it was naphthalene, not benzene, right? Benzene would just be 1 ring. Naphthalene would be 2 rings like that, right? So if I have this naphthalene here reacting with this and HNO3, H2SO4, predicted product for these 2 naphthalene reactions here. What would we include in a Diels order mechanism? So the Diels order mechanism is very simple. It's very short, right? Because if we go back to number 12 here, all there is to a Diels order reaction mechanism are these 3 concerted arrows here, right? So the mechanism for Diels order is 1 concerted step like that, creating this cyclohexene product. And all Diels order reaction will always create a cyclohexene product. But the trickiest part for Diels order is the endo rule and where the groups are supposed to be aligned. The regiochemistry of it, which is the charge alignment, and the stereochemistry part of it, which is the endo rule. Oh shoot. For number 12, aren't both products and the answer key actually the same thing? So number 12 right here, right? They would technically be different because there's no plane of symmetry here, because these chiral centers here would be different. Like the green chiral center here with the nitrile group is different, and the purple chiral center here is different as well. Because if I were to assign RNS, this is going to be priority number 1. This is priority number 2. This is priority number 3. And going this way, it looks S, but it's actually R because the lowest priority group is a wedge. So we flip it to what it actually looks like. So this right here is an R. If I assign priority for the other carbon, this is 1, this is 2, this is 3. So this one here, it looks R, but it's actually S, because the lowest priority group here is a wedge. So we have to flip it to whatever it looks like, right? So that's why they're different. But for Helix class, don't worry about that. He just draws out one of them, even though you get 2 different enantiomers here, right? So like if you just draw this one set of enantiomer here, you still get full credit for Helix class. But they're actually different because there's no planar symmetry here, and the chiral centers of these groups would be different. You could also test the same for the purple chiral center here. They would be different as well. Yes, so that includes the enantiomer, but that would also flip this enantiomer as well. So like this would be wedge, this would be dash, and that would also change the chiral center of these carbons as well, right? These right here are diastereomers of each other. Like this plus minus here is showing the enantiomer version, which every single chiral center flip, right? But these sets are diastereomers of each other because this chiral center here stays the same, whereas this chiral center here, like, they're wait, actually no, they're different stereochemistry. Wait, hold on, let me see. So this is wedge dash. Yeah, wedge. Yeah, so yeah, these are diastereomers of each other because like you would see that these chiral centers are the same, whereas these chiral centers are flipped, making them diastereomers of each other. So going back to naphthalene here, try this predicted product out, these 2 predicted products out right here. Why does the E not attach to ortho for the first one, for EDG? Why does the electrophile not attach to the ortho for the first one? Yeah, so the E would not attach to the first one because of steric hindrance. That's going to be the minor product. It would prefer the para product because that's major, right? There's less steric hindrance there. Okay. So yeah, I could go over number 17 after. These practice problems can be found on the Discord. I could send it here as well. Let's see. File, computer. And here's the note card as well. Here's the note card. And here's the practice worksheet. And here's the winter 2023 Helix exams. I don't have it right now, but I will download it and send it to the school website later. Right. So I'll go over number 17 after. That includes enantiomer. Would a halogen substituent be for naphthalene be considered an EWG or EDG? It's the exception orthopara inductor instead of meta, but technically still an EWG. So yeah, a halogen would follow this EDG pattern as well, because halogens are considered weak EWGs, but they're not meta directors. They are orthopara directors. So because of that, when you see a halogen on naphthalene, right, attach the electrophile opposite to the halogen, right? So I'm gonna put EDG/X, where X is gonna be chlorine or bromine, the halogen. And for EWG, would you get a mixture of top and bottom additions? You would get the bottom one addition here because of less steric hindrance. The top one here would increase more steric hindrance, and if you draw out the resonance structures, this is going to be the most like resonance stabilized form, right? So this is just a pattern thing here. Like the major product would have the bottom product only, right? For the practice, would they add the opposite since the directing group is an EDG? The directing group is an EDG. Yes. Correct. Right. Are there other meta products with EWG substituents? So when we have EWG substitutes on naphthalene, the electrophile is going to attach on the other benzene ring on the opposite side. If you have an EWG on a benzene ring, just a regular benzene ring, then that's a meta director. Except for halogen, right? Except when you have a halogen, the halogen is an orthopara director. Yep. Okay, so Sharon, you got bromine attached to the other opposite end. That's good. Right, because we have an EDG attached to the naphthalene. So when we do this naphthalene reaction, we're going to attach the electrophile opposite to the EDG. Now, for the second one, we have an EWG on the naphthalene. So we're going to attach the electrophile on the other ring on the opposite side, right here. That's correct, right? Now, here's a tricky thing, right? A lot of people see these esters here and they get confused about like the differences between them, like how to tell if it's an EDG versus an EWG. And to tell that, right, look at the very first atom coming off of the system. The very first atom coming off of the system of this first reactant here is the oxygen, which is partial negative charge, and it has pairs of electrons that I could use to directly donate electrons into the system, making that an EDG. Whereas the very first atom coming off of the ring here, or the system here, is this partial positive charge carbon, which is going to withdraw electrons directly, making that an EWG, right? So that's how we tell the difference between this ester and this ester. Look at the very first atom coming off of the system. If it's an oxygen with a pair of electrons, EDG. If it's a carbonyl carbon, EWG. Yeah, so bromine here is going to be across this EDG here, because when we attach the bromine here, when we draw out the resonance structures of this, that's the most resonance stabilized intermediate. We wouldn't attach it ortho to it because that's too much steric hindrance. And we know this is an EDG because the first atom coming off of the system here is oxygen with a pair of electrons, donating electrons towards the ring. And looking at this pattern right here, if we do EDG on the naphthalene, the electrophile will attach on the opposite carbon across from the EDG, which we see here, right? This is our EDG on this naphthalene. So when we do this EAS reaction, we're going to attach the electrophile on the opposite carbon from the EDG. Yep. Okay. Would you recommend we just use that note card info on our own? Yeah, so this document I made for last year's 2Ts, it includes all the reactions and mechanisms you need to know, except the naphthalene ones, right? Because the naphthalene ones are like pattern recognition for predicted product. You don't even need to know the mechanism for it. Like this is just most likely going to show up as one predicted product at most, right? It might not even show up, but this is going to, like, it might show up. So just know that pattern recognition, when you have an EDG or halogen, the electrophile is going to attach across from it. If you have an EWG, the electrophile is going to attach across from it, but on the other benzene ring. So that's what you're probably going to get for naphthalene. But everything else is included in this note card. The reaction mechanism, and reaction and Diels order and everything. So you could print it out and everything should be there. What happens if halogen isn't in that position? if halogen isn't in this position, then that would be the minor product. Like if you put halogen here, 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 or here, or any other carbon, that would be the minor product. Can you go over number 11 and 19? Yes. Is there any way you can provide more Diels order ring opening? Yeah, there's more Diels order and ring opening, ring closing reactions in the worksheet. We can go over that. Relating to my question from earlier. So this one right here, we have naphthalene and a chlorine on that carbon. Right, and that's the key. So we put chlorine on that carbon there. So Helix didn't go over that type of naphthalene reaction where he put that substituent on that position. He, on his lecture slides, you won't have to worry about that on the exam, right? Because I'm looking at his lecture slides right now, and he just went over these two patterns right here, where he put the group on this carbon or this carbon only, because that's where the group would be more stable at from the naphthalene. He didn't put the group on that carbon at the left carbon, so you don't have to worry about that for Helix's midterm, right? But if that's the major product, I would recommend you guys draw out the resonance structure of the intermediate and see why that's going to be the most stable resonance stabilized structure. Yep. Yeah, so I wouldn't overwhelm you guys with that information if you guys don't need to know it for the exam. Just focus on what Helix is going to test for this midterm.
Yeah, he has an IC for you.
Okay.
Okay, bye.
Bye.
Okay, so let's go over 17 and then 11 and then 19. Let's do, oh, before we do that though, let's finish off this ring opening, ring closing reaction. We did ring opening already with the thumb rule. Now we're gonna do ring closing here, right? And the ring closing arrows are gonna look like this. We're gonna move that double bond over there, shifting this double bond over here. When we do that, we're gonna make a single bond over here. And this is gonna be my atom number 1. This is atom 2. This is atom 3. This is atom 4. So that's gonna give us this product right here, where this is atom 1, this is atom 2, this is atom 3, and that's atom 4 right there. Right, now we see at carbon 2, it is sp2 hybridized and it stays sp2 hybridized. So that methyl group is going to stay flat and planar, no wedge, no dash there. But at carbon 1 and 4, it converted into an sp3 carbon, which is going to have stereochemistry now. It's going to have a wedge or dash, right? So now we're going to use the thumb rule. Because we have 2 pairs of electrons, which is an even pair of electrons, with light, H nu, we're going to have a dis-rotatory reaction. So let's write that down so that we don't forget. This rotatory reaction, right? Now we look at this chart here with the thumb rule. Because we're ring closing, I'm going to start my thumbs left or right, and I'm going to end my thumbs up or down. And I'm going to rotate my thumbs clockwise or counterclockwise. Okay, so now to do this right here, I have to look at the direction difference between the group on 1 and 4. Coming off of 1, that group is going up. Coming off of 4, this group is going down. So I know that they're going on opposite directions of each other, right? So now, because of that, I'm going to start my left thumb going left, my right thumb going right. They're going on opposite directions because they're going on opposite directions here, right? This ethyl group is going up, this methyl group is going down. So I'm going to start my left thumb left, right thumb right. My left thumb is going to represent the ethyl group. My right thumb is going to represent the methyl group. So now, if this is dis-rotatory, let's say I rotate my left thumb clockwise. That means that I would have to also rotate my right thumb clockwise, right? Going this way, yeah, clockwise, like this, right? So we see one is going up, one is going down. So that means that this ethyl group here is going to be wedge going up. This methyl here is going to be dash going down. We could have done it the other way. If I rotated this thumb counterclockwise, I would have to rotate. Wait, hold on. I think I'm doing something wrong here. I think I rotated the wrong direction. So if I rotated this thumb clockwise, that means this thumb would have to rotate counterclockwise, going this way. Yeah. So I rotated it incorrectly. So that should be the answer, plus minus, right? Because if I rotate my left thumb clockwise, because this is this rotatory, I have to rotate my other thumb the opposite direction, counterclockwise, and they're going in the same direction now, right? But if I rotate my left thumb counterclockwise, I would have to rotate my other hand clockwise, opposite direction. So they're gonna both face down. So they're either gonna be both wedge or both dash. So a common misconception here is that when people see this rotatory, they always think that the two groups are gonna be trans to each other, but that's not true, right? This rotatory or conrotatory just shows you how you rotate the groups, what direction to rotate the groups at. Right. Okay. So that's the procedure for ring closing, which I would say, in my opinion, is easier than the procedure of ring opening, because there's a sneaky bond here that counts as a pair of electrons, right? And also, we have to keep account for the minor and major product. Whereas for ring closing, we just have to do it once and do plus minus in enantiomer. But ring opening, we have to do both directions to see the minor product versus the major product. Okay, now let's do the questions that you guys asked for, which is going to be 17, 11, and 19. So let's do 17. Okay. So 17 right here. So I have this group right here reacting with heat. What do you guys think is going to happen? Can you show the mechanism for number 1 as well? Yes, I can show the mechanism for 1 as well after I go over 11 and 19. So if we have this group here with this alkene and 2 groups with this heat, what's going to happen here? We're going to do ring opening. Yes. So right now, this alkene here is not going to do anything with the heat. But this right here is going to do ring opening like this. And I just noticed here that 4-membered rings here are only able to open in light. So that's just a conceptual thing. So keep that in mind. But that's more of a Nisiri and Levin's question, right? I don't think Helix went over that, but a 4-membered ring here is going to open up in light only, not heat, right? But just in theory, let's say that it's able to open up in heat. So if I number this 1, 2, 3, 4 like that, if I open up the ring, it's going to look like this S cis diene right here, right? And because this is an even pair of electrons, that's going to be reacting with light. That's going to be, what is it? Let me copy and paste the table down here for ring opening, ring closing. Right? So this right here is going to be even pair, heat, con, rotatory. So let's do the thumb rule. Ring opening. 1 thumb is going up, 1 thumb is going down, because we have 1 dash, 1 wedge. So because this is con rotatory, let's say I rotate my left thumb counterclockwise. I would also have to rotate my right thumb counterclockwise, and they're going on opposite direction now, right? So that's gonna have this methyl group go up like that, and this methyl group go down like that. If, however, I rotated my thumb clockwise and my other thumb clockwise, they're gonna bump into each other, which could also be a product, but that's a minor product, right? So this is a minor product here. This is a major product here. Yes, 4-membered ring here opens up with light, right? Whereas the other membered rings, like let's say you have this membered ring right here, opens up with light or heat. It can open up in light or heat. Right. And this is going to be S cis because of the orientation that this ring was already in. When we open up the ring, it's already going to open up in the S cis configuration, right? Where this is atom 1, this is atom 2, this is atom 3, this is atom 4. So when we open up the ring, it's going to already be in that position, the S trans configuration. And I can highlight that for you here, right? If this is the 1, 2, 3, 4 right there, that's this 1, 2, 3, 4 right here. Yeah. Okay, so now we're going to use the major S-cis diene here to react with this molecule here. And based on these two molecules with heat, what do you guys think they're going to do with each other? What reaction? Diels order, yes, because this is my diene, this is my dienophile here. And the charge alignment is already there, right? Because I have an EDG here, an EDG here. So I have a partial negative charge on this carbon, a partial negative charge on that carbon, right? And I have two EWGs on this dienophile, giving us a partial positive charge on that carbon, a partial positive charge on that carbon. So we don't have to worry about regeochemistry here. The charges are aligned already. So when I draw that bubble between the diene and dienophile, the pocket between the diene and dienophile, right? That helps me identify what my out and in groups are. I have two out groups here, those two methyl groups. There's no in groups, right? You could consider the hydrogens as in groups, but that's invisible. We don't have to worry about that. And we have two EWGs here. We have this EWG and we have this EWG here. So when I draw out the product, that's the template for Diels ordered product. That cyclohexene, where this is atom 1, this is 2, this is 3, this is 4, this is 5, this is 6. Now let's say my outgroups are dashes. To follow the end of rule, they have to be cis to the EWG. But there's two EWGs here, the one CN on top and one CN on bottom. So only one of them can follow the EWG then, because these CNs here are trans to each other, and we have to maintain that trans configuration. So if I chose my top CN to be dash to follow the endo rule with the outgroup, my bottom CN has to be wedge. It's forced to become wedge because the dienophile is trans, right? This alkene is trans. So we got to maintain that trans configuration right there. And that's going to be plus minus, right? And I think if you just put that, you get full credit. Don't worry about drawing the other one. Right, so this number 17 right here, wait, for Helix class, right? But for Levin's class, you would have to draw the other one because Levin's would look at the stereochemistry, but for Helix class, if you draw that, you should get full credit. You don't have to flip it upside down. Now, this number 17 here was an electrocyclic ring opening reaction and the Diels order in one question. Right, we first opened up this ring to get the S-cis diene, and then we did Diels order with the dienophile to get this Diels order product here. Okay. Now let's do number 11 and 19, and then number 1. 11. So the mechanism for number... Oh, wait, no, I did number 11 already. Let's do number 19. Did we do number 19 yet? Let's see, number 19. Number 19 right here. Okay. What reaction do you guys think is gonna happen here if you see this reactant molecule and this reagent? Pyrrhocalves, yes. Pyrrhocalves, alkylation or acylation? Acylation, because we have this acyl group, correct? Which is gonna be my electrophilic carbon, my dot, right? But usually we see the acyl group on the reagent arrow. In this reaction, we don't see the acyl group on the reagent arrow. We see the acyl group on the same molecule as the benzene, right? And in EAS reactions, the benzene is the nucleophile. So we're going to do an Friedel-Crafts acylation reaction, right? So we're gonna make a ring here, and we want to make a stable ring. So let's say this is my electrophile. I can make a 1, 2, 3, 4, 5, 6-membered ring if this carbon here is my nucleophile, right? So I'm just gonna show you guys how to predict the product quickly for this intramolecular Friedel-Crafts acylation reaction choice. And if you guys want me to go over the mechanism, I could go over that after. But let's say this is just for predicted product. I know that I'm gonna make a 6-membered ring from this 1, 2, 3, 4, 5, 6-membered ring right there. So when I draw out the product, it's gonna look like this. Where this is atom 1, this is atom 2, this is atom 3, that's atom 4, that's atom 5, that's atom 6. Atom, now that's gonna connect my star and dot bond, right? This is the new bond that I created between them. There was no bond between 1 and 6 before, but we made that new bond when we closed the ring. Now everything else is copy and paste. Decoration. 4 has the isopropyl group. 5 has the methyl group, and 6 has the carbonyl group. The chlorine here leaves in the mechanism. It leaves as a leaving group. And that gives us this final answer here. Right? And this is going to be a sneak peek of what we're about to do later when we go over mechanism. But let's say I convert that molecule into this molecule here. What reagent would do that? And I'll give you guys a hint. There's 3 reagents you could do. You could use to convert that molecule to this molecule here. Right? And it's going to be a sneak peek of what we're about to do with synthesis. H2PDC, yep, a reducing agent, such as H2PDC. Or you could have used iron, HCl, or you could have used the Clemmensen reduction, zinc, mercury, HCl. Any of these 3 reducing agents would reduce the carbonyl into this alkyl group here. Yes, FeHCl would work as well. Let's say you had this though, and you wanted to go back. Wait, actually, no, you can't do that because you would have to like convert both the benzylic carbons to the carbonyl. Right, so let's say you wanted to convert both these carbons here coming off the benzene ring, right? That's called the benzylic carbon. The first carbon coming off of the benzene ring into the carbonyl, carbon double bond oxygen. What reagent would do that? Jones, yes, CrO3, H2SO4, and water. Right, and that's very important because that's gonna interconvert our groups from ortho para director to meta director and back and forth. And that's gonna be very important for synthesis. But we'll go over that after I go over your guys' questions here. So, someone wants to go over the mechanism for number 1, so let's do that. Yes, so this number 1 reaction here, what kind of reaction is this? What's the name of this reaction for number 1? Friedel-Crafts alkylation, yes. And specifically, this is an intramolecular Friedel-Crafts alkylation. Right? Now, here's going to be the mechanism because someone asked for the mechanism. This Cl here is going to attack this aluminum because that aluminum has an empty p orbital. It's missing 2 electrons. When that happens, we are going to form this intermediate right here. This aluminum has a negative charge, this chlorine has a positive charge, and we're going to think of this as our good leaving group now. Right? Now, usually, for Friedel-Crafts alkylation, we form a carbocation. We cannot kick out that leaving group by itself, because if that leaving group leaves by itself, we're going to form an unstable primary carbocation, right? If that was a secondary carbon or tertiary carbon, that leaving group can just leave by itself to form the stable carbocation. But because this is a primary carbon here, it cannot leave by itself, right? But what we can do is a concerted hydride shift. So what we're going to do instead is draw out the hydrogen here explicitly and shift that hydrogen over to this carbon and kick out the leaving group right there to give us this stable tertiary carbocation, right? That's why Friedel-Crafts alkylation is the hardest EAS reaction in terms of mechanism, because there's different scenarios in the mechanism depending on what your alkyl group is, right? Because it could either do a regular hydride shift it could do a concerted hydrate shift, or it cannot do any shifts at all. Right? In this case, we're doing a concerted hydrate shift to form this stable carbocation right here. And if I want to make a stable ring, 1, 2, 3, 4, 5, 6, this would have to be my nucleophile here. It could have been this as well, but I'm going to choose this as my nucleophile. So that's going to be my star right there. So I'm going to have this starred molecule carbon attack that dot carbon to give me this 1, 2, 3, 4, 5, 6 membered ring, which is going to look like this right here. This is my star molecule, this is my dot molecule, and this is the new bond between the star and dot molecule right there. Now everything else is decoration, right? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. 6 has 2 methyl groups like that. This carbon here lost a bond, so it's positively charged. We broke the aromaticity of the structure here when we added the electrophile, right? Now the third step here, the last step, is to restore the aromaticity by drawing out that hydrogen explicitly coming off of the starred carbon. And our base here is going to be this AlCl4, right? Where the aluminum has a negative charge. One of the chlorines here is going to be negatively charged and attack that chlorine and do an E1 type mechanism to restore the aromatic ring, to restore our benzene ring and form that ring right there. HCl is a side product. AlCO3 metal catalyst gets reformed in the mechanism. That's why this AlCO3 can be reused in another reaction, right? But HCl gets formed as a side product. And this is our final answer here for intramolecular Friedel-Crafts alkylation, right? In all EAS mechanisms, there's 3 steps. The first step is that you form an electrophile. And once you form the electrophile, you do addition. But when you do addition, you break the aromaticity of the ring. And to restore the aromaticity of the ring, you do elimination to get that double bond back. For ring opening and closing, can you go over how to tell whether the product would be con or dis? Yeah, so to tell whether or not the reaction will be con or dis, you have to look at how many pairs of electrons are moving and the conditions you're in. So if you see this ring opening reaction here, we see 3 arrows of electrons, which is an odd pair of electrons, and you get this chart right here. And because we are in light, we have convolatory. So it's all based on this chart right here. Right? If you are ring closing, we have 2 pairs of electrons here. For this specific example, which is an even pair of electrons reacting with light, that's disrotatory. So this chart here is very important for that reaction to tell whether or not it's going to be conrotatory or disrotatory. Okay. Any questions on the mechanism on number 1 here for this intramolecular Friedel-Crafts alkylation reaction? Okay. So before we go on to synthesis, I did have questions from my private tutees that I want to get over based on this stuff. So let's go over that. Smazna and Zibia still here. Nah, I could just go over the questions and send them the thing after. So yeah, okay, so they have a question on synthesis, so we could go over that later. Zibia here. Okay, this is on the ATC worksheets. So, okay, yeah, I'll answer them on that later. And Aaron. Okay. So, any questions before we move on to synthesis problems and helper reactions? Any other questions on this worksheet? Okay. Yeah. So before we move on to the synthesis problems, let me show you guys these reactions here. How to not mess up with in-out group orientation when flipping molecules in those other reactions. Number 16. Okay, yeah, let's see. Yes, so I'm gonna go over number 16 after I go over the benzene substituent reactions before we do synthesis. Right, number 16 is gonna help with that. So I'll go over number 16 after. Oh, number 14, same as well. Number 14 and 16 are gonna be about the benzene synthesis. So these are gonna like be the warm-up for the synthesis problems that we're about to do. For number 1, how do you know which carbon to make the nucleophile on the ring? Yes, so for number 1 right here, I know that my nucleophile has to be either this carbon here that I just starred or this carbon here. It could have been that carbon as well, because that would form a stable ring, a 6-membered ring. 1, 2, 3, 4, 5, 6. It couldn't be this carbon because it would form a very weird ring because of this structure right here, right? Any other carbon would form a unstable ring. The one that would form a stable ring would be that carbon or this carbon here, right? If you chose the top carbon as a nucleophile, your ring would look like this instead. Wait. Boom, 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 like that. Ignore that. So this would be your 6-membered ring instead, but the 6 carbon is gonna have 2 methyl groups like that, right? So that's how you choose the nucleophile. You see which one would make your more stable ring. So are you trying to choose the carbon closest to the chain as well? Yes, you could think of it like that. The carbon closest to the chain for this specific reaction to make the more stable ring. Yeah, of course. Okay, so Emily asked how to not mess up with the in or out group orientation when flipping molecules in Diels autoreaction. So that's a good question, because I remember in one of Helix's exams, he drew out one thing like this and one thing like this right here, reacting with heat. Okay, so in Diels autoreaction, we said earlier that the S-cis diene does the reaction, not the S-trans diene, right? But we see an S-trans diene in this molecule here, and this is my dienophile right here. So to convert this S-trans diene to the S-cis diene, we have to rotate this single bond right here. And we're able to do that because that's not part of a ring. If that single bond was part of a ring like that, we could not rotate that ring. And this diene could not do a reaction. There would be no reaction with Diels auto here. But because this is not part of a ring, we can actually rotate that bond to create us this S-cis diene right here. Right? And now, based on this right here, we have 2 EDGs. This EDG and this EDG. Which EDG do you guys think is gonna be the stronger one? And that is gonna like give us the charge that we're gonna be worried about for regiochemistry? The top one, correct. Because the top one has pairs of electrons that can donate electrons directly into the system. So when we draw out the resonance structures, there's gonna be a bigger negative charge on this carbon right here. Right? This R group here is also an EDG, but it donates electrons inductively. So there's going to be a smaller negative charge here. So we're not worried about that. Now, I'm just going to specifically draw you out the NO2 group out like this, specifically, right? And the reason why I'm doing this is because I'm going to draw out the NO2 out in a slow structure. There's a full-on negative positive charge on the nitrogen here, making that an EWG, right? So when we withdraw electrons from the dienophile system, there's going to be a positive charge on that top carbon right here. So the way that I drew it, if I draw the pocket or the bubble between the diene and dienophile, we see that the charges are not aligned. So we cannot proceed with the Diels auto reaction right away. Right? That is not good. We got to flip one of them upside down to align the charges. Right? We could either flip the diene upside down or we could flip the dienophile upside down. I recommend flipping the dienophile upside down because it's smaller and it's easier to redraw. Right? That was like quicker to draw than the diene, where there's going to be a partial positive charge down here now, and the diene is going to stay the same. I'm not going to flip the diene, right? And now we see that the charges are aligned. The negative charge and positive charge are on the bottom, right? And then we could proceed with the same Diels order reaction, giving us this product here, right? And there's a methyl group here as well that I drew, which was cis to the NO2. So I'm gonna draw that methyl group there as well. Right, and that's the final product for this Diels order reaction here. What happened to the other methyl group? Yeah, I forgot to draw that out. That methyl group is still there, right? Which is cis, right? This is an alkene. Don't forget about alkenes from midterm 118B, right? This is a cis alkene, so we gotta maintain that cis configuration. This methyl group here stays cis to the NO2, right? And this is my out group. This is my out group, which is gonna be cis to this EWG based on the endo rule, right? So if I made my out groups dashes, this EWG would also have to be a dash to follow the endo rule, right? Now on the dienophile, I have the NO2 and methyl group cis to each other, and I have to maintain that cis configuration between them. If the NO2 is dash, the methyl would also have to be a dash. In question, the methyl is an EDG. Yes, the methyl is an EDG. Right. This carbon here does have a negative charge, right? Because the methyl is an EDG, so if it donates electrons into the system, this carbon would also have a negative charge, but it would have a very small negative charge compared to the negative charge down here, because this OCH3 here is a stronger EDG than the methyl group. This EDG is an EDG by resonance because it can directly donate electrons into the system by giving it electrons, full electrons. This R group here has 0 pairs of electrons. It just donates electrons inductively, weakly. This is a weak EDG. This is a strong EDG. The NO2 is a EWG. So dienophiles can have an R group as well, right? But they're going to have a strong EWG, right? Like if you see dienophile, they can have a strong EWG, but they can have a weak EDG, like an R group, and that weak EDG would be able to be there for the dienophile, right? But we need that strong EWG on the dienophile, because for Diels order reaction, right? Here's a conceptual thing. For Diels order, the diene is the nucleophile. The dienophile is the electrophile. So to increase the reaction rate, we have to put an EDG on the diene, and we have to put an EWG on the dienophile, because the EDG would give the diene more electrons, making it a stronger nucleophile. The EWG would withdraw electrons from the dienophile, which would make the dienophile more positively charged, a better electrophile, right? So if there's a stronger EDG on the diene, that increases the reaction rate. If there's a stronger EWG on the dienophile, that increases the reaction rate, right? This dienophile here does have a strong EWG, but it can have that weak EDG there as well. Do you automatically assume that EWG will put partial positive on the furthest alkene carbon while EDG puts... Yes, on the dienophile. Yes, you can assume that. Can you discuss question 3? Yes, I can. After these questions. So wouldn't the strong EDG have more of a partial negative charge because it can donate electrons? Yeah, so this is a stronger EDG here, but the negative charge is on the opposite end, right? Because when we draw out the resonance structure of this, let me actually draw that out for you to show you why there's a negative charge on the opposite end. So let's say I have this diene here with this OCH3 right here and the methyl group right here. This pair of electrons is going to go down to make a double bond there, shifting this double bond over there, which shifts this double bond to make a pair of electrons on that carbon, giving us this resonance structure here, right? And if I highlight my diene backbone, which is that right there, I see that there's a full negative charge on this carbon here, coming from this EDG. So that's why there's a negative charge on this carbon, which came from that EDG right there. Will both ends be equally charged with equal? Yes. Yes. If there's equal EDGs, like what we did earlier, like let's say we had this diene with 2 R groups, both ends would have equal negative charges like that. Can you send the Helix 20 when you have the time? Yes, I can send that later when I have the time to, right? But I have to download it from my drive and find it. But if not, it's gonna be here, yeah, right. Okay, so let's discuss question number 3. So number 3 here is Diels order. right? Where this is my diene backbone, this is my dienophile backbone. Now, Helix didn't really go over the differences in like the electron withdrawing group power of dienophile, like dienophile. So I wouldn't worry too much about this for Helix class, right? Because this would give us a major minor product, but Helix didn't really go over that for Diels order. So I wouldn't worry about this question here. But if you want to do it, like there's gonna be a negative charge here. This CN here is a stronger EWG than this aldehyde, so there's gonna be a bigger positive charge here. So the charges do align. If I draw the pocket between the diene and dienophile, this is my out group. This is my in group. These are my EWGs. So if I draw out the template of Diels order, it's gonna be like that, where the out group is gonna be dash, let's say, and it's gonna be cis to this EWG. And because the CN is cis to the aldehyde would also have to be dash as well. This ethyl group would be wedge. And this in group right here is gonna be wedge, like that. Right? And another way that you could visualize this product is this right here. Right? This is just another way that you can see the molecule, where you could easily see the bicyclic ring. Like you can see the two rings there, one ring there, one ring there. Okay, plus minus. Can you draw the dienophile resonance? Yeah, so this right here, I could draw the resonance here with the nitrile. Right, so I'm gonna explicitly draw out the nitrile like this, where the carbon has a triple bond to nitrogen like that, and this nitrile here is a stronger EWG than that aldehyde, so it's gonna withdraw electrons from the dienophile like this. Right, this double bond here is gonna shift over to make a double bond here, which is gonna pop one of the bonds of the triple bond onto the nitrogen to give me this resonance structure here. Right, where if this highlighted portion is the dienophile, that's the highlighted portion of the dienophile, where we see a full positive charge on that carbon right there, which is why there's a positive charge on this carbon right here. So the negative charge is always on the opposite of the EDG for dienes. So that's only true if the diene is on the end of the if the EDG is on the end of the diene like this. So if there's an EDG, only one EDG on the diene, then that's true. The negative charge will always be on the opposite carbon, right? If the EDG is on the bottom here, then the negative charge will be on the opposite carbon. It would not be true if you have an EDG on the middle carbons like this, right? Because the EDG would then donate electrons into the ring like that and push the double bond over there, which would create a negative charge on that top carbon instead, right? So when you have an EDG on the inside carbon of the diene, then there's going to be a negative charge on the closest carbon to that EDG, right? If you have a diene where the EDG is right here instead, then the negative charge is right there. Yes, we give preference to the stronger EWG because the stronger EWG would withdraw that double bond more strongly than the weaker EWG. Yes, question number 3 is right here. Yeah. Oh yeah, Cyrus had a question too. I forgot he sent it to Cyrus. question here on the synthesis. Yeah, so these are coming for the synthesis problems. Okay, so I'll finish up with the synthesis, like the predicted product synthesis problems and the synthesis on this worksheet. Okay. When do we look at EWG strength versus electronegativity of atom, oxygen versus nitrogen? So you would always use the electronegativity strength, right? Like the EWG strength for diene, dienophile, and even benzenes, right? And the list is given here for you, where this is a strong EDG, this is moderate EDG, weak EDG, weak EWG, moderate EWG, strong EWG. So look at these groups here to determine what's your what's the stronger EDG, what's the stronger EWG. Right. Okay. That only applies to benzene, not linear alkene. Benzene, not linear alkene. Like, do you mean dienophile for the linear alkene? If you have a dienophile here with multiple EWGs, you would look at the EWG strength to see which EWG would withdraw the alkene from the dienophile. If this is the stronger EWG, based on this chart, then the positive charge would be down here. Yeah. So it does not only apply to benzene, it applies to dienophiles as well. Okay, yeah, let's do number 9. Yeah, so number 9 right here, CF3 is a stronger EWG than this carboxylic acid based on the chart. So the positive charge is up there. We have an EDG right there, which is going to put a negative charge on this carbon right here. We also have EDGs here and EDGs here, but because we have an extra EDG here, the negative charge is going to be on that carbon right there. So the charges do align. So when I draw the pocket between the diene and dienophile to determine my out and in groups, this is my out group. This is my in group. These are my EWGs. Okay. And that's going to give me this cyclohexane product, where the carbons in the middle here stay flat and planar because they're sp2 hybridized. This in group here is going to be a CH2 connecting 1 and 2, like that. This out group is going to be a dash ethyl, which is going to be cis to these EWGs. So I'm going to make them dashes as well. And because this ethyl group here is like trans to this carboxylic acid, I'm going to make that ethyl group wedge, like that. Plus minus. You've like messed up the drawing for these. Yeah, what's the hardest part for you? Like when you draw these products, like is it the ring or is it the EDG, EWG? Yeah, so I could run it slowly. I'm gonna number this 1, 2, 3, 4, 5, 6, which is gonna be this 1, 2, 3, 4, 5, 6. So the yellow highlighted part is this yellow highlighted part right here. That was the diene. The blue highlighted part is this blue highlighted part right there. The red highlighted part is the new bond between the yellow and blue. Right, that's the new bond between them. Carbons 2 and 3, those groups stay flat and planar because they stay sp2 hybridized. Right? And then carbon 1 and 4, they have that in group right there connecting them, which is a ring right there, that wedge right there, that CH2 right there. So if you wanted to highlight it, let's highlight it green. This green part right there is that green part right there. And then this is the out group on carbon 4, which let's say it's dash, which has to be cis to the EWGs. So these EWGs here would also have to be dashes, right? And at carbon 5 right here, we have the ethyl group as well, which is trans to the carboxylic acid. So because the carboxylic acid here is dash, this ethyl group here would also have to be wedge, right? Because they're trans to each other. Yeah. So the other way that you can see it would look like this. Right? Where this is the yellow part, this is the blue part. These are the new bonds between the yellow and blue part. This is the green ring between 1 and 4. And everything else are decorations and groups based on the endo row and the dinophile configuration. Yeah. I always have a hard time with the endo rule. I think I got it now. Yeah, so the endo rule, like the most important thing that it states is that the out group here, facing outside of the pocket, is going to be cis to the EWG, right? Whereas the in group is going to be trans to the EWG. Right? That's the endo rule for your Diels order. Which one is the major and minor product? So both of these here are the same, right? So this is the major product here. The minor product is if you were to flip these groups around, like if the carboxylic acid was down here instead, and the CF3 and ethyl group was up here instead, that would be the minor product. But we don't have to draw that for predicted product, right? And you won't have to worry about it for Helix's class because Helix doesn't give you multiple EWGs on the dienophile like that to compare. He just gives you like one EWG for one positive charge, right? If the dienophile was tetra substituted, how do you apply the endo rule? To apply the endo rule, like if it's tetra substituted, for leave-ins, you're gonna have like 16 different products for Diels order. So you don't have to worry about that. For Helix class, just worry about the one EWG, right? So don't worry about the tetra substituted multiple EWG for the dienophile, right? Because you're gonna have like many different products, if that's the case. Yeah, so let's look at the answer key for number 9. Oh, I updated the answer key for number 9. Right. I think you have the old copy right here. This right here is the new copy where this is the major product because the CF3 here is a stronger EWG than the carboxylic acid. So because that's the case, there's a bigger positive charge there. There's a big partial negative charge here. They align, right? But this right here, when you compare the strength of EWG on the dienophile, right? That's gonna be for more leave-ins in this series, like test. Helix will only give you one EWG on the dienophile for one positive charge. So you won't have to worry about comparing the EWGs on the dienophile like that. Yeah. Yeah. Yeah, so question 3 here. This is major because CN is a stronger EWG, positive charge there. EDG, negative charge there. When we do the endo rule, this is going to be cis to the EWGs, and the in group is going to be wedge, trans to the EWG, and this ethyl group here is trans to the CN, so that's why it's trans to the CN right there. Right, and this is major because the CN here is a stronger EWG. This is minor because the charge alignment is not great here, right? There would be a positive charge here and a negative charge up here. They don't align very well. That's why that's the minor product. But for Helix class, you won't have to worry about this type of problem for Diels order. Yeah. Number 9. Okay, let's do synthesis problems. So before we do that though, I'm gonna go over these helper reactions and then predict the product related to these. If I have this group right here, is this an ortho-para director or a meta director? Ortho-para director, right? Because it's an EDG. I can convert that ortho-para director into a meta director by oxidizing the benzylic carbon. This first carbon here coming off of the benzene is called the benzylic position, benzylic carbon, right? So to do that, the reagents to use are Jones, CrO3, H2SO4, and water. Now, would this group be an ortho-para director or meta director? Meta director, yes. Okay, now let's say we want to convert this meta director carbonyl into this alkyl group here. We went over this earlier. To do that, we could use any of these three reducing agents, H2PDC or FeHCl or ZnHgHCl, one of these three reducing agents. Okay, that's very important for synthesis, especially because the order of the reactions that you do in synthesis is important because of the ortho-para director and meta director, and also Friedel-Crafts reactions do not work on deactivated rings, right? So that is important to know as well. And also the sulfonate, like para position blocking group as well, is important. So if I have, let's say, this group right here and this group right here, what's the difference between these two? The first one is a meta director, correct? Because that's an EWG. And the second one is an ortho-para director because that's an EDG, right? And you're gonna notice that NO2 is one of the strongest EWGs. And the red one, NH2, is one of the strongest EDGs, right? And you can say that this NO2 here is the oxidized form because it has more oxygens. And this NH2 here is the reduced form because it has more hydrogens. So if we want to convert an NO2 to NH2, we got to reduce it using the reducing agents H2PDC or FeHCl or ZnHgHCl. Now, if we want to oxidize the NH2 to the NO2, we got to use an oxidizing agent CF3CO3H, which for Helix, he might draw it like this instead on the arrow. So if you see this is CF3CO3H, right? But if you do practice from AATC, Levens, Mario Jones, you might see MCPBA, right? That MCPBA would also oxidize the NH2 to NO2. But thinking back to midterm 1, what did MCPBA do to an alkene? Like what reaction does MCPBA do to an alkene from midterm 1, the alkene midterm? Yes, it makes an epoxide ring, right? But we have 3 alkenes here, right? How come we did not create an epoxide ring from these 3 alkenes? Like, how come we didn't have, like, let's say this epoxide here, we got rid of that double bond? Wait, we're going this way, so like it's supposed to be here instead if we did MCPBA, right? Because we're going this way. Resonance, right? These double bonds here are doing resonance with each other and they're aromatic. We don't want to disrupt that stability, right? It's very stable. It's by resonance and aromaticity. It's aromatic and we don't want to break that aromaticity, that conjugated system. Can Friedel-Crafts happen on slightly deactivated rings? Yes, Friedel-Crafts can work on slightly deactivated rings. So for example, if you have a benzene here with a halogen, like Br, you could do a Friedel-Crafts reaction. Right. If you have a benzene with a strong EDG and an EWG SO3H, you can also do a Friedel-Crafts reaction. Right. But even though this SO3H here is an EWG, a deactivator, making this ring deactivated, we have this strong EDG countering that, right? So if you have a strong EDG here, like a strong EDG, this Friedel-Crafts reaction can still happen, right? This is especially important because we can like get rid of that SO3H group by desulfonation with dilute H2SO4 and water, which I'm going to go over after. but Friedel-Crafts reactions can work on slightly deactivated rings. A benzene stable aromatic. Yes, that's why we don't get the epoxide there. What's the limit? So if you have no EDGs, or for example, let's say we have, let me put this up here so I can add another page. If we have this benzene ring here with just NO2, a strong deactivator, and we try to do a Friedel-Crafts reaction, Friedel-Crafts alkylation, let's say, no reaction happens, right? This is strongly deactivated. If we have SO3H on the ring and a methyl group on the ring, well, because this is a synthesis technique, I could see how you could still do Friedel-Crafts reaction here, because this SO3H here is commonly used to block the para position, right? Which we could go over later. So SO3H here is an interesting one because you would actually have to ask your professor, but Helix, most likely, he allows you to do Friedel-Crafts reaction as long as there's an EDG right here, right? So you can still do Friedel-Crafts there, but if you just have the SO3H alone on the benzene ring with nothing else, and you try to do Friedel-Crafts reaction, no reaction. Okay. Yes. So let's go over that. Actually, the para position with the sulfonation reaction. So if I have this benzene right here, and I have this group, and I want to synthesize this right here, what steps would you guys say would carry this synthesis route out? Can you add 3 equivalents of SO3 to occupy all ortho para positions? So you can do that, right? Like if you put 3 equivalents, you could put like SO3 here, here, and here. But that's going to be very unstable, because if you have 3 groups like parallel to each other, like adjacent to each other, I mean, next to each other, that's like a lot of steric hindrance. So that's like not going to be formed like a lot. It's very low yield because of steric hindrance. But you technically can in theory. So try this synthesis problem out. How would you carry this synthesis problem out here? What would you could either go backwards retrosynthetically, right? Or you could go forward. Right? What is the relationship between this group and this group here? Are they ortho to each other, meta to each other, or para to each other? Ortho to each other, yes. And what is this group here? Is this an ortho para director or meta director? Ortho para director, yes. So when we try to do chlorination with CO2, AlCO3, this is going to be in low yield, right? Because the high yield product will have the chlorine on the para position. But we do not want the para product at all. We only want the ortho product, right? So we cannot do chlorination as the first step, because that's going to lead us to the product in low yield. To get to this product in high yield, we have to block off this para position. To block off that para position, we're going to do sulfonation. SO3, H2SO4. Yes, block para position, add chlorine, and then desulfonation after. Correct, right? Because once you block off that para position with SO3H, then you could do chlorination, CO2, AlCO3, to add the chlorine group ortho to this EDG right here. And then to get rid of that sulfonate group, we use dilute H2SO4 and water to get rid of that SO3H group right there. Okay. So let's look at this one here. We had two substituents on the benzene ring, but why did this group here direct where the electrophile went? Like, why didn't this SO3H group? Well, actually, it did kind of, because like this SO3H group, this is the meta position to that. But let's say we have this group here. I'm gonna give you guys 3 examples here. Okay, so let's say we have these 3 rings, and we try to do an EAS reaction to all of these 3 here. And the problem here is going to ask you which group is going to be the directing group. Right, let's look at the first one here. Would the directing group be the isopropyl group or the SO3H group? The isopropyl group, correct? Because it's a weak G. This often is a strong EWG, right? So any EDG would take priority over an EWG, right? Don't get like too confused on the strong and weak, right? The weak EDG will take priority over the strong EWG, because the EDG here activates the ring more, making the ring more nucleophilic. So this is the direct ortho or para to it, right? Now let's focus on these 2 here. What would be the directing group, the methyl group or the N? Okay. Yeah, so for the second one here, what would be the directing group? Would it be yes, it would be the NH2, because the NH2 here is the strong EDG versus the weak EDG. Now, for the third one here, what would be the directing group? The NO2 or the aldehyde? So let's look at the chart here of the strengths of EDGs and EWGs. NO2 is a strong EWG. A carbonyl is going to be a moderate EWG. Right? And if we have multiple substituents, we want to choose the group that has more activating power. Right? So a strong EDG takes priority over moderate EDG over weak EDG. And then weak EWG takes priority over moderate EWG. And the least priority group is the strong EWG. Right? So look at the last example here, which is the trickiest one. We have a strong EWG versus a moderate EWG. And the moderate EWG here is the one that's going to direct the group because it does not deactivate the ring as much, right? We want to choose the group that has the more activating power, which is the weaker EWG, So the activating group is this aldehyde here, which is gonna direct the electrophile meta to it. So it's gonna be here or here. It cannot be here because it's already taken by the NO2. Yeah. So let me highlight the ones that are the priority groups. That would be the directing groups. Right. So if you have multiple substituents, choose the substituents that has the better activating power, the better activator. If you have two EWGs, choose the one that does not deactivate the ring as much, the weaker EWG. Okay. So now there's one more benzene substituent reaction that I want you guys to know about, which is the aniline and phenol thing. Aniline and phenol. So aniline here is gonna be this benzene with NH2. Phenol here is gonna be this benzene with alcohol here. When we try to do like Friedel-Crafts reactions to these, right? Let's say, for example, we try to do this Friedel-Crafts acetylation reaction to this aniline and phenol. Usually, the benzene ring is the nucleophile for EAS reaction. But NH2 and OH here is a stronger nucleophile than the benzene ring here, right? So instead of the acyl group attaching onto the benzene ring, we're going to attach the acyl group to the NH2 and OH, right? Which is going to give us my amide and ester here. Don't worry about the mechanism. That's going to be 118C. If you guys have to take that, this is the beginning of 118C, right? So the important thing here is that if you have aniline and NH2 on the benzene ring or phenol and OH on the benzene ring, and you try to do Friedel-Crafts reaction, it would not attach onto the benzene ring. It will attach onto the nucleophilic nitrogen atom or nucleophilic oxygen atom instead, because those nitrogens and oxygen atoms are stronger nucleophiles than the benzene ring itself, right? So let's say you did want to attach the acyl group to the benzene ring though. You have to weaken the nucleophilicity of the NH2 or OH. You have to make it a weaker nucleophile. And we could do that by these reagents here. We could convert NH2 to an amide, which is a weaker nucleophile, by using acyl chloride and pyridine, right? And this is a weaker nucleophile because if we look at the pair of electrons on the nitrogen here, ignoring the benzene, the pair of electrons on the amide can do resonance with the carbonyl. And from 118A, the resonance makes things more stable, which is going to make it less reactive. Yes, this will be posted on YouTube soon. I do have a session at 11:30 to 12:30 today, so I'm going to end the session at 11 so I could get ready for that session. But it will be posted after that session, probably. Right. So that's why, because this amide here is stabilized by resonance, it's a weaker nucleophile, right? Because more stable things are more happy, they're less reactive. So from this structure here, no, not for this class, it's good, it's for a different session, for a private session, private session, right? So now we can do the Friedel-Crafts reaction from this weakened nucleophile, which will attach the acyl group to the benzene ring now, right? Now, if you want to deprotect it, we are going to use NaOH and heat, right? Which is going to deprotect this group to the NH2 right there, right? I don't have it downloaded on my computer right now, but I have to look through my Google Drive, but I will post it to this website here, right? The Helix 2023 exams after this session. Yes, I do sleep. I'm gonna sleep right after. I'm gonna sleep right after. My last session. Yeah, you could find it in the classroom tab in the winter 2025 module, and it's gonna be in the review session class. Right. Yeah, it's gonna be winter 2025 module in the classroom tab. Okay, so now for phenol with the alcohol here, we can protect the alcohol and convert it into an ether. And this is going to be Williamson ether synthesis from 118A. And that's going to be NaOH CH3I, right? And you do know mechanism for this, but you don't have to worry about that because that's not tested here. But what's basically happening here is that the OH minus is deprotonating the alcohol to create the alkoxide ion, the O minus ion, which is going to attack the CH3 and kick out the iodine to give us this OCH3 right here, right? Now, from this point, we know that the ether is more stable than the alcohol, so it's less reactive, so that we could do the Friedel-Krauss reaction from the ether, right? And then from there, if we want to get back to the alcohol, we can deprotect it using concentrated HI, right? All of these helper reactions that I just went over here are included in the note card with the mechanism right here, right? We could protect the NH2 to amide using these reagents and going backwards, phenol to ether going backwards, oxidation and reduction of the alkyl group and carbonyl, oxidation and reduction of aniline and nitrobenzene, and then protecting the para position with the sulfonation reaction and desulfonation reaction. So all of that is included in this section, this bottom right corner of the back page of the note card. Okay. Now, assuming that you guys already know the 5 EAS reactions like nitration, sulfonation, halogenation, and Friedel-Krauss alkylation, acylation, we could do the synthesis problems now. Yeah, I haven't posted it yet. I will post it like sometime after my session, like probably like 12:30-ish a.m. I have to look through my drive for it, right? Yeah, of course. So let's do the synthesis problems here. Do you guys want me to guide you guys through it by asking questions, or do you guys want like some time to work on these synthesis problems here? Or are there any like synthesis problems that you guys wanted to go over? Like any questions on this you guys wanted to go over? Number 4, 2. 4, 2, 5. Okay, let's do 4, 2, 5. So 4, right here. 7. What reactions from 1:A will be on the midterm? Oxidation reduction, Grignard reagent reaction, SN2, SN1, E1, E2. Those are the main ones. Epoxidation, MCPPA, that's for midterm 1. But the main ones are redox reactions, Grignard reactions, and SN1, SN2, E1, E2, and acid-base reactions, right, from 1:A. Number 4 right here. We have 3 substituents coming off of this benzene ring here. This halogen, this R group, and this carbonyl group here. This halogen is a weak, well, let's not even, yeah, this is a weak EWG. This is a weak EDG. And this is a moderate EWG. Right, the carbonyl. The R group is a weak EDG. And like we said earlier, if you have multiple substituents, then you want to choose the substituent that has the higher activating power. And which one would that be? What group would that be out of these 3 groups? Bromine here is a weak EWG. This carbonyl here is a moderate EWG. The EDG here has the strongest activating power, the R group, right? because it's an electron donating group. Electron donating groups will take priority over all EWGs. So this is my directing group here. This R group right here. And that R group is an ortho para director. So if I cross out the ortho and para positions to show you where they are relative to that EDG, these are the ortho positions, that's the para position. We cannot add anything to this ortho position because it's already taken. We don't want to add anything to this ortho position because that's going to add 3 groups adjacent to each other, and that's not good. We do not want 3 groups adjacent to each other. That's very bad. That's sterically hindered, right? So the only open spot for us to add is this para position right here, right? And that's lucky for us because what do we see here? We see this group para to this EDG. What EAS reaction do you guys know that would add a nitrogen atom to the benzene ring? Nitration, yes, HNO3, H2SO4, the reagents for nitration. And that's gonna add the nitro group para to that weak EDG, the directing group, right? Now, there's one last step here. What can we do to reduce the NO2 to NH2 and reduce the carbonyl to the alkyl group here? There's 3 reducing agents you could use in this last step. H2PDC, correct. So I'm accounting for ortho meta para by like this. So this is my group right here, right? I'm ignoring every other group. I'm not looking at any other group. These are my ortho positions relative to that group. This is my meta position relative to that group. This is my para position relative to that group. So you can think of it as OMP, Ortho is the first carbon away, meta is the second carbon away, para is the third carbon away, OMP, right? I'm ignoring the other substituents because they're not my directing group. I'm looking at the ortho meta positions relative to this group right here, which is my directing group. Right, like just ignore everything else. That's a distraction, that's noise. And you look at the ortho meta positions relative to this group right here. Right, and the green axis here, that's ortho. Wait, the one I just X'd out. And this is para right here. Okay. Let's do number 2 right here. I have an empty benzene ring with 0 substituents. And I want to get to this benzene ring with 3 substituents. There's many different directions we could go, many different orders we can go, right? But what do you guys notice the relationship between these 3 groups are? Like, what's the relationship between those 3 groups? They're all meta to each other. Yes, so we know that this is going to be meta directing synthesis like all throughout, right? Now, which one of these groups do you think could have been the meta director? The azo group. So the NH2 group here, right, is an ortho para director. But if you were to look at the NO2, that's a meta director, right? So we can do that, right? But which one would you guys want to do first? Do you guys want to do nitration first? HNO3, H2SO4 to add NO2 to that carbon? Or do you guys want to do Friedel-Crafts acylation first to add this azo group? Yes, and why do we want to do acylation first and before nitration? Like, what happens when we do nitration first? Like, can we add the azo group after? NO2 won't do Friedel-Crafts. Yes, nitration will stop Friedel-Crafts reaction, right? This NO2 here will deactivate the ring, and when we try to get to like this group right here, that's no reaction. We cannot do that, right? So that's why we cannot do nitration first, because the nitration will deactivate the ring, making it unable to do Friedel-Crafts reaction, right? NO2 can't do phytocaps because NO2 is the deactivator, the electron withdrawing group. NH2, if we try to do phytocast reaction on the benzene ring, it can't add the acyl group to the benzene ring because it would add onto the NH2 instead. Right? So basically both can do phytocast acylation on the benzene ring because NO2 would deactivate the ring, giving no reaction. Whereas NH2 here, when you try to do phytocast acylation, the acyl group would attach onto the nitrogen instead of the benzene ring. Right? So you gotta protect the NH2 like we did earlier and deprotect it afterwards. Yes, we gotta do nitration after. But like why didn't we do phytocast alkylation? Like why couldn't we do this as the reagent right there? There's two reasons why. Carbocation shift, right? Which is gonna give us this as my intermediate here, and therefore this as my R group, right? And also, is this an orthopara director or meta director? Orthopara director, right? And we don't see anything orthopara here, so that's no good, no good. So we're gonna do phytocast acylation first to add that acyl group right there. Okay. Now from here, like someone said earlier, we could do nitration said second, right? Like A said we could do nitration set second, which would add the NO2 group meta to this acyl group, like that. Okay. Now, what else can we do to add, like, let's say this chlorine group here? It's gonna be like, do we have to change any directing groups, or can we just straight up add the chloride with chlorination with Cl2 AlCl3? Like, is it perfect here? So H3O plus second step will be needed for phytocast acylation. If you do phytocast alkylation with AlCl3, no acid workup is needed. You don't need H3O plus. This all happens in one step. But phytocast acylation here, it does have that acid workup step. Right, for phytocast acylation. Alkylation, no acid workup. Acylation, acid workup. Yeah. Yes, we have to do that Cl first, chlorination first. We can't do H2PDC, right? Because if we do H2PDC, we're gonna reduce the NO2 to NH2 and reduce the carbonyl down right here. And which one would have the high priority group, directing group, NH2 or the R group? Which one would be the directing group if we reduced it to NH2 and alkyl group? NH2, yes, because that's a stronger EDG, and that's an orthopara director, right? And now I'm gonna ignore that and X out the orthopara positions relative to that NH2, right? If we do chlorination, the chlorination major product is gonna be there, the para product, because that's the least sterically hindered side. We don't want to add it here because that's gonna give us 3 groups adjacent to each other. That's not good. 2 sterically hindered. This is gonna be the minor product because we can add it there because that's not 2 groups next to each other, but that's steric hydrogen still, right? But we don't even want the chlorine here or here, so that's not good. So we gotta do chlorination first when we have the meta directors in place. But here's just a conceptual thing here. What would be the directing group here? The strong EWG NO2 or the moderate EWG carbonyl? What would be the directing group? Moderate EWG. Yes, moderate EWG. It's not going to be the strong EWG because the strong EWG deactivates the ring so much. We want to choose the group that does not deactivate the ring. We want to choose the group that activates the ring a lot, right? So it's going to be the moderate EWG. In this case, it does not matter because they're both meta. If let's say the NO2 was ortho here, it would matter, right? But that was just a conceptual question to have you guys thinking, like, if you guys have to choose between 2 EWGs, right? And if you guys have to choose between 2 EWGs, choose the weaker EWG as the directing group. But in this case, it didn't matter because they're both meta, right? So that would be chlorine there, NO2 here, carbonyl here, and to get to the final answer, H2PDC for the synthesis. Can you add chlorine before nitration? Because both could be on meta position. So if I added chlorine here before nitration, like let's say with CO2 AlCO3, I would have this benzene with the acyl group and chlorine right here. And now, which one would be my directing group? This moderate EWG or this weak EWG? Which one would be my directing group? So if we are comparing two EWGs to each other, do we want to choose the weaker EWG or the stronger EWG if we're comparing two EWGs together? We want to choose the weaker EWG. So my directing group here is the chlorine because that's the weak EWG. And this chlorine here is an exception. It's not a meta director. It's an ortho para director. So if I X the ortho and para positions, those will be the positions where the NO2 is not going to be in any of these positions. So that's why we got to do nitration first before chlorination. But NO2 is stronger than the other one. NO2 is stronger than the other one. Like, are you talking about this one right here? Yes, NO2 is a stronger EWG than this moderate EWG, right? But when we choose between the directing groups, if you're comparing between two EWGs, you want to choose the weaker EWG, right? Like, if there are multiple groups on the benzene ring, choose the strongest activator to be the directing group. An EDG is known as an activator because it donates electrons into the benzene ring, making it a stronger nucleophile, activating the ring. An EWG is known as a deactivator because it withdraws electrons from the benzene ring, making it less negative charge, more positive charge, making it a weaker nucleophile. Right. So if you have multiple groups, you choose the groups on the left side over the right side. So a strong EDG would take priority over a moderate EWG, which would take priority over a weak EDG. Right? Like strong EDG over moderate EDG over weak EDG. Now, if you have EWGs, a weak EWG would be higher priority than a moderate EWG, which would be higher priority than a strong EWG. So a strong EWG here has the lowest priority when we choose the directing group, right? That's because the strong EWG here deactivates the ring so much, right? And when we choose the directing group, we choose the directing group that activates the ring the most, right? So if you're comparing two EWGs, you choose the weaker EWG. Right, so if we go back to the synthesis panel here, when we're comparing this strong EWG to this moderate EWG, the directing group would be the weaker EWG, which is this one here, right? But it doesn't really matter because they're both meta director and then meta to that is the here, right? But it doesn't matter there, right? So that's why like we gotta do nitration first instead of chlorination, because when we do chlorination, the chlorine group is a weak EWG, the carbonyl is a moderate EWG. And based on what we just talked about, the chlorine is gonna be the directing group because it's a weaker EWG, but it's gonna direct it orthopara, right? Because halogens are the exception. Even though they're EWGs, they're not meta directors, they're orthopara directors. And we don't want the NO2 in any of these positions right there. Right. Okay. Yes. So that's all I have time for today's review session. I'll post the session as soon as possible, probably after like around 12:30ish after my session. But yeah, good luck guys. I'll post these to the school, and if I have time, I'll post the extra practice to the school website as well after my last session. Yes, I'll post it to the website. Yeah, of course. Good luck guys.
Will you be able to post the note card as well?
Yes, I will also post the note card as well to the school website. Like everything will be there: the note card, the notes, and the Helix exams 1 to 23.
Okay, thank you so much.
Yeah, of course.